This is Jim Hendershot again, lecture number 36, entitled Some Manufacturing Processes Worth Discussing for Electrical Machines. We're going to talk about some specifics, not everything, but some things that might be unusual to you and should help your understanding of the manufacturing process to help you in the design. It's been said that good products have to be designed for manufacturing, so that's what this is all about. This is a slide here that shows that's by a company called Mitsui High-Tech. They're a Japanese company, and the top part of this slide is a flow chart for the normal manufacturing process of stators for these kinds of machines. And we don't have to go through the whole thing, but there's the rotor line here, and then there's a stator line here, and there's 10 steps for the stator and 4 main steps for the rotor. Wait a minute, I got these backwards. The rotor has all the steps. The stator has fewer steps. So you can go through these, but that's a lot of steps. And this company, Mitsui High-Tech, they replaced that manufacturing process with a one-step stator manufacturing method. They stamp the lambs from there's a coil of steel, they stamp the lambs, and they get stacked cores coming right off the lambs. And the case of the rotor, they do pretty much the same thing with the rotor, eliminating all these steps. And this involves punching the lambs with these nesting dimples in them, so that after you punch the lamb from the strip, it's pressed against the last one that was punched, and they are nested together with an interference fit of these little dimples that are accurately punched in there. And normally the manufacturing method at the top, classical methods, means that you either rivet the lambs together, you bond them together. Of course, they're hand stacked or automatic stacked for riveting, but when you bond them, they're usually hand stacked using tooling to stack them accurately and hold them accurately in place while they're bonded. They can be staked, they can be cleated, laser welded, TIG welded, and the process used in the bottom here, the MAX system, is defined as the interlocked core stacking method, direct from this punching die. We talked about this before. The cores then for the housing for the stator are either press fitted or shrink fitted into the stator cores. There's actually been some production where the stator housing has been aluminum die cast right around the core, just the same way that rotors are die cast with aluminum. There's companies in Europe have done that, and I'm sure Japan and other places. I don't know if any Americans actually die cast a finned aluminum frame or housing around the stator core. I'm not sure. But if there's excessive radial forces from that, it reduces magnetic properties of the lambs, which we talked about before. Use of adhesive to attach cores to the frame, we talked about that. That eliminates press fitting or shrink fitting. And you can also use anti-rotation screws. Big, large frames sometimes have no housings on them at all, or they have housings with big spaces between the OD of the core and the ID of the housing, and big keys in there. And but by the main point here is, as we stated in the last lecture, that it's important that the ID of the laminations be concentric to the pilot diameters on the frame where the end belts locate. The rotor construction, we've talked about that many times. For permanent magnet machines, surface mount magnets have to be retained so they don't fly off with sleeves or pre-stressed yarns. We've talked about loose bars or no-nos, and we've talked about the fact that certain bar designs are not suitable for inverter duty. Here's some pictures of different manufacturing process of small stators. We can go through these. Here you stack the lambs, and they've been TIG welded here, TIG or laser, nice small welds. They should be over the center of the teeth, and they're not, though. They're beside the tooth. That's not a good idea. But these have been insulated with an epoxy coating, as has this one been insulated with an epoxy coating. It's also on the ID, where this one it's not on the ID. And then, so after the core is insulated with either epoxy coating or slot liners, then the coils are wound automatically on a machine in sets. There's, like this is an example, there's 3 coils per phase. This must be a 4-pole 12-slot motor. So this would be phase A, this is phase B, and the finished wires are connected to the start wires of the next coil, so there's no interconnections required in these random wound coils, and they can be hand inserted or automatically inserted in the slots and overlapped, high-low, lap winding, and then the lead wires, if there's lead wires which are a larger gauge than the magnet wire, this shows a single strand per turn, but sometimes you have multiple strands per turn, and so you crimp or solder the magnet wire to a stranded lead wire of larger gauge, so the lead wire doesn't hang up, and because sometimes these lead wires are very long. And then the end turns are blocked or formed in dies that don't damage the winding insulation, and then they're laced, and they have automatic lacing machines that lace these, or they can be laced very nicely by hand to restrain all those, and then it's varnished. At some point you have to test the phases. You can build a little automatic test fixture that can actually be part of the fixture that you use, the staging fixture you use to solder and connect the lead wires can be the same as a test fixture. It can be tested on the same machine. This shows the lacing, forming of end turns and lacing. This is shows some pictures of the automatic machinery used to wind stators, and this can be used for all 3 motor types we're talking about. You have the core stacking and stacking by automatic, and this is a TIG welding machine. Then you have a machine that takes a roll of the Nomax or Mylar slot liner material, a roll of it, and it goes on this machine. The core goes on this machine, and each piece is cut and formed with cuffs on it and inserted down the slot, and this goes as fast as a machine gun. Then you have automatic phase coil windings. This is called a shed winder. They're wound in one station, and they're dropped on these fingers, and these fingers go in the slots of the stator core. And then this is inserted over this arbor here, and this is the stator core, and this is pushed forward into that, and the pushing of these fingers down the slots drags the opposite. It drags these coils right down in the slots and inserts them in the stator, and then they're formed and lead wires. There's no picture of that, of how they're. Oh, here's a picture. Here's the end turn forming here. These are dies that in a press that will form these end turns and get them ready for lacing. Then you fuse the lead wire to the magnet wire, and then this is automatic lacing machine, an amazing mechanical mechanism that laces the end turns, and then it's the end or the tire slots impregnated with varnish or epoxy or something or trickle varnish, one of those processes to retain. This is automatic. This equipment costs millions of dollars, and you need a separate set of tooling for every size stator. And you're also limited by how much slot fill you can get from this automatic insertion method. Probably 35% is as high. They like to do only 25% slot fill, but they can do up to 35. If you go higher than that, I think you have to hand insert. Although I see that Ford Motor Company is building a traction motor for their electric vehicles that they claim with this similar type equipment as this, they're getting up to 70% slot fill, but they add some other stations to put in only part of the turns per slot, and then they force them back in the bottom of the slots with drifting dies and then hold them there by the interns while they put the next set in, so they're able to get a higher slot fill by adding extra tooling. Now let's look at some stator configurations. This is a stator of a small motor that's, I think we've looked at this before in another tutorial, but here's some more details. This is a strip of steel that this is stamped out of, all these teeth, and they're stamped so they're hinged together. And so what this does for you is you can take that all hinged together and put it on a piece of tooling on a winding machine, and then this is a fly winder. Here's your magnet wire that comes around over there, and this is fed back and forth here to layer wind and build up the coils as you see here, and they're hinged backwards so you can get out all the coils. And then after all the phases and all the coils are wound, the starts and finish are connected to these pins that are molded in the bobbins that go around here. See, there's nylon plastic bobbins that go over the teeth, and the pins for the wire termination are sticking out there. And so you, after this is all done, you wrap it up the other way and you make a stator out of it. And you get high slot fill from that. We saw pictures of that before. Now this is the slinky method of stator core manufacturing. It's a very old method. It's called the Pavesi method, and yet the original form of this was designed by General Electric and patented by them years and years ago. And you have big roller dies that take strip stock like this and punch the two strips, the teeth of one nest in the slots of the other. So you get two of one here. Very little waste. There's no scrap or very little waste here. And the roller dies are over here, and it feeds down here, and they're edge wound. Like they're edge wound right here, and then they're all the teeth are all lined up with this edge winding, and then they're welded. And I'm not sure. I guess you have to see punch strips, storage mechanism, coiling mechanism, I guess that's this, winding mechanism, coil conveyor system, final coining mechanism, finished cores. I don't know what final coining is. I don't know what that is, but they're wrapped up essentially like this, like a slinky clamped together with the teeth all lined up, and then they're welded on the OD. Those are awful big welds. They don't need to be that big. And then, of course, they're automatically inserted with these cuff slot liners ready to put the coils in. Actually, the way the coils are put in, I couldn't find any pictures of it, but that is an amazing machine that winds the coils, that puts them in all three phases. It's an incredible. I'm still looking for good pictures to put in this later through a revision. If I find them, I'll add them. But this is a die-cast rotor. I showed you the problems with this. A very poor job. The bar cross sections have been almost cut off completely, which gives you high cage resistance. And I would make these end rings thicker than this to reduce the resistance in the end ring. That will help suck the heat out of the bars. I don't know why they're so stingy here. The cost of aluminum isn't that much to add a little extra aluminum on the end. I think that's a poor design. Well, that concludes our series of lectures here. I think there's one more. I plan to present some challenges for the future for motor design. That'll be the last one, and I'll get that one prepared soon here. So thank you for watching.